The purpose of this video, which accompanies Chapter 2 of Modern Database Management, is to illustrate how to analyze a business situation and discern database requirements from it. I think you'll find data modeling somewhat like solving a puzzle or a mystery. It may not be CSI, but I think you'll still find it fun. Hi, I'm Jeff Hoffer, one of the co-authors of Modern Database Management. This video shows a reasonably simple, yet surprisingly rich situation, one that hopefully will help you become comfortable with the basics of data modeling. You can use this video to review what you have read in Chapter 2 of Modern Database Management, or alternatively, you might find this video helpful as a preview to the chapter and to what you will be able to do after studying the chapter. You see on the screen a typical description of data needed in an organization, in this case a college campus student organization, much like those to which you belong. In many ways it reads like a description of the club. That's not surprising, because not only do data tell the status of an organization, but also a description of data, what we call metadata, explains the nature of the organization and the rules that govern data in the organization. However, such narrative descriptions, being in native language, are typically imprecise, incomplete, and possibly contradictory. A lot like some homework problems, right? Our job as data modelers, not at all an impossible mission, is to create a precise, complete, and consistent description using both diagrams and very structured text to supplement the diagrams. That's what you will learn to do in Chapter 2. So you ask, where do you learn what the data requirements are for an organization? A textual description such as that shown here might be found in official organizational documents. For example, business plans, annual reports, or statements of needs for an information system. Other times these narratives, often in outline form, are notes you've taken during interview sessions to elicit requirements for a new information system. In any case, one or more documents like the ones that we've just seen are the kind of input available to you as a data analyst or database designer when you are beginning to develop a model for the data needs of an organization. And this is typical of problems and exercises in modern database management and those you will be asked to solve on exams. So you'll soon have a chance to flex your own data modeling skills. The most common form of data modeling is entity relationship diagramming, which is a way to model organizational data without being tied to one technology for building the information system. A simple ERD data model, taken from Chapter 1 and unrelated to the previous narrative description, is shown on the screen. This entity relationship diagram consists of entities, the rectangles, which represent the objects of the organization, relationships, the lines, which represent associations between the entities, and attributes, listed within the rectangles, which are the characteristics, the data, about entities. One or more attributes of each entity is an identifier, meaning no two instances of that entity have the same value for this attribute or attributes. An analysis of an organization's requirements for data can lead to new ER diagrams from a clean sheet of paper, or can result in enhancements to an existing data model. In this video, we will work from a clean sheet of paper, and we will assume that the description we displayed a moment ago defines all of the data needs of the organization. We will show in this video how you can study such a description and evolve from your analysis an entity relationship diagram to describe the data for that situation. Such skills are at the core of being an information systems professional, or even an information systems user who needs to understand the system to be built for you. There is no one way to develop and draw an entity relationship diagram, or ERD. Two general approaches are studying each sentence to find the elements of the ERD, building up the ERD from each of these pieces, or more of a gestalt approach of reading the whole description, finding all the possible entities, then reread the description to find additional elements for the ERD. In either approach, nouns in the description help us to identify the entity types, as well as the attributes and identifiers for each entity type. And verbs suggest relationships between the entity types. You'll see how all this develops as we work through our example. We can draw an ERD on paper. Please use a pencil, a whiteboard with a clean eraser, or a flip chart with plenty of paper. But because of the iterative nature of drawing the diagram, we'll need to be prepared to make lots of changes. A better approach is to use computer software. Computer-aided software engineering tools like Oracle Designer, Irwin, Visible Analyst, and even Visio are sophisticated applications that maintain a variety of drawing types and other metadata for documenting not only data, but also processes, flows of data, and decision and event logic. We show and compare the notations used by several popular tools that specialize in drawing entity relationship diagrams in Appendix A of the text. Alternatively, you can use multi-purpose drawing tools, which include an ER diagramming component. One such software, SmartDraw, is used at many universities and is available as an optional bundled software with modern database management. We will demonstrate ER modeling in this video using SmartDraw because it is rather versatile for drawing ERDs, and its ERD notation is very close to the tool neutral notation we use in the book. Of course, your instructor will specify which tool or tools you should use in your class, and no one software is best. It is, in fact, good to learn several tools and their slightly different ER notations because you will encounter a variety of tools in your profession. So, let's begin. Take a moment to read this brief paragraph. As I mentioned earlier, there is no one way to analyze a situation description to determine the database requirements. We'll begin, as we just did, by reading the whole statement to get a general understanding. Then from that understanding we can list or draw the entities mentioned, and then analyze each sentence to fill in more details about attributes and relationships required. From reading this whole situation description, we see that we will need data about members and events, and maybe more. So, we can start our ERD by placing member and event entity types on our ER diagram. Entities are given singular noun names, so the entities are member and event, not members and events. The description that we've seen tells us that for our student club, the club needs to keep track of the name, email address, and major of each member. So let's add to our entity relationship diagram these attributes of member. Because other entity types in our diagram might also have attributes of name, email, and major, I've chosen to prefix each of these attribute names with member. This is a good naming convention. We discuss in Chapter 2 thorough guidelines for naming all the elements of an ERD. Each entity type needs an identifier, values for which distinguish one instance of that entity type from other instances. But our description does not indicate what that identifier might be for member. It is possible, even if unlikely, that two or more members would have the same name, for example, George Foreman or Mary Smith. So we can't depend on name to be the identifier. Email addresses are unique, but people can change their email address, say from a campus account to a Gmail account. We really don't want the identifier value to change. And, of course, more than one member is likely to have the same major. So the best thing to do in this case is to create a surrogate identifier, one that does not have a meaningful value in this campus organization. For lack of a better name, we'll call this member ID and add this to the attributes of member. We indicate an identifier by underlining it, which is a common way to specify the identifier. And because identifiers are required, we also make member ID bold, which is a common way of specifying an attribute that must have a value for every instance of that entity type. It is unclear from the description whether the other attributes are required or optional. So to keep this example simple, we'll leave them optional. Let's look at the next sentence. Each event is given a unique title and has a date and location where that event occurred. From this sentence, we know the attributes event, and we know that title is unique, so it can be the identifier. Let's add event title, date, and location as attributes event on our entity relationship diagram. We'll assume that event, date, and location are optional because an event might be planned before a date and location are set. But in practice, we'd have to investigate whether this is a rule for our campus organization and database. But we'll go ahead and make event title the identifier and, of course, required. Now that we have described members and events, maybe the next sentence will tell us something about a relationship between these entities. The next sentence says, a member may attend many events, and an event may be attended by many members. This sentence is a classic statement about a data relationship. We know from this sentence that there will be a relationship, which we will call attends, from member to event. It is good to give relationships names in both directions. However, SmartDraw does not support this feature. You can see examples in Chapter 2 for naming relationships in both directions. Cardinality is the number of instances of an entity type that participates in the relationship. Cardinality has nothing to do with birds or the Catholic Church. Fortunately, the sentence is clear about cardinalities for attends. It says, a member may attend many events. So there will be a minimum of 0 because of the may word, and potentially many events associated with a member. And it says an event may be attended by many members. So there will be a minimum of 0 and potentially many members associated with a member. This is a binary, optional, many-to-many relationship between member and event. To show this in SmartDraw, we can select the relationship line and then click on the custom option within the arrowheads and select the notation for each end of the relationship. Let's look at the next two sentences that address organizing events. An event is organized by one or more members each of whom plays some role in organizing that event. A member may never help organize an event. This is a little more complicated statement about the relationship between members and events. Also, we note that this sentence discusses a separate relationship from attends, which we previously drew. It's not unusual to have multiple, independent relationships between the same pair of entities. Let's start by simply drawing a relationship for organizing events by members. Because of what the sentences say, we know some member has to organize an event. That is, an event is organized by one or more members. But some members may organize no events, or potentially many. So we can draw a suitable many-to-many relationship between member and event, which we'll call organizes. You'll notice that it has placed cardinalities on this line. But what we want is that an event has to be organized by at least one member, but that a member may organize many events. So we need to change this cardinality. That's easy to do. We'll select that line, go into the arrowheads again, customization, and we will change the notation to a member must organize at least one event. Well, that's wrong. So the arrowhead is selected at the wrong end. So we will change this one to the required and this one to the optional. And now we have the cardinality that we want. What we have not yet shown is the role the member plays in organizing an event. It is not clear whether a given member always plays a specific role in all events they help organize. For example, when a given person helps to organize an event, she always arranges for the band. If this were the case, this would be another characteristic of each member, and we'd add an attribute of role to the member entity. But this is very restrictive, although we don't know for sure what the situation is. We'd have to ask some questions, which is part of the data modeling process. In fact, this is the part I think you'll find most fascinating, even empowering, about data modeling. The success of data modeling really comes down to making no assumptions and being impertinent to ask all kinds of questions, like, is that always true? For example, could two different events have the same title? Are there any exceptions? For example, for the first time the event occurs? And might you want to do things differently? For example, could there be related events? And all kinds of other questions. To illustrate a common data modeling situation in this video, let's assume that each member can play a different role each time they help to organize an event. Thus, the role is not a characteristic of a member, nor is it a characteristic of an event, because different members may play different roles for the same event. So role is really a characteristic of a relationship instance between member and event. Most ER drawing tools do not allow us to put attributes on relationships. Well, that's okay, because we can create a new associative entity to hold this role name attribute. And in a moment, we'll replace the organizer's relationship with this associative entity. We'll call this associative entity organize and give it an attribute of role name. Notice that SmartDraw provides a separate symbol. the rectangle with the rounded corners, to show an associative entity. Many drawing tools and even many specialty ERD drawing tools and case tools don't distinguish associative entities from strong entity types. You may have also noticed the rectangle with a double line, which is used for weak entity types. So, how do we relate organize to member and event? Each organize instance is for one member helping to organize one event. So we can draw relationships between member and organize and between event and organize. Because a member may never help organize any event, a member may not have any associated roles, but could have potentially many associated organize instances. An organize instance is for exactly one member. So we can place a 0 to many cardinality next to organize coming from exactly one member, which is exactly what we have. Because an event is organized by one or more members, the cardinality next to organize will be 1 to many coming from event for exactly one event. Well, that needs to change. So we will come up here to arrowheads and customize that, and rather than the optional many, we will have the required many or mandatory many. Notice what has happened compared to the organizer's relationship. We moved the cardinality next to event on the organizer's relationship to the cardinality next to organize coming from member. Similarly, we moved the cardinality next to member on the organizer's relationship to the cardinality next to organize coming from event. This is what happens when we convert a many-to-many relationship into an associative entity. We could put names on the relationships that associate role with member and event, but the associative entity name serves this purpose. And these are not two separate, independent binary relationships, but really the result of one many-to-many relationship that was converted to an associative entity. Now we can delete the organizer's relationship and rearrange the diagram to make it more compact. You'll recall that we delayed talking about an identifier for organize. So far, all we have is an attribute of role name. The meaning of an associative entity is that there is an instance of that entity each time some member helps to organize some event. Thus, the same role name value, for example, arranged speaker, may appear several times for different members organizing different events. We could make up some surrogate identifier for the organized entity, like we did for member, but rather we'll take a different, default approach for organize. Because each organized instance is about some member, identified by member ID, and some event, identified by event title, we'll assign no explicit identifier to organize. Surprised? In this case, implicitly organize then has member ID and event title together as its identifier, what is called a composite identifier. We don't need to show this on the ERD. No two organized instances can have the same pair of values for these attributes. This is a default approach for any associative entity, that is, to inherit as its identifier the identifiers of the two or more strong entities it associates. So now our entity relationship diagram is complete. We had to make some assumptions, which in practice we'd have to investigate to get it exactly right instead of assuming. Before we finish, let's consider one refinement that might not be obvious and isn't even necessary to make this ER diagram a precise, complete, and consistent description of the campus student club situation. But I've got your attention and we're having fun, so let's go for it. A potential data integrity hazard within this diagram is that the same role may get different names each time a member serves that role for different events. This is because each time an organized instance is created, a separate role name attribute value is specified, and we can't be sure the same name will always be used for exactly the same role. We can add some control to the data model of this situation and to the database that will contain data about the situation if we create role as a separate strong entity type with an identifier attribute of role name. Now, we will eliminate role name from organize and relate organize to role. We can eliminate role name from organize because we can find the role name for an organized instance, the role played by a member for an event, by following a relationship from organize to role. As we relate organize with role, we know that each organized instance is for exactly one role, and we can assume that each role may be played by more than one organize. That is, we'll assume there may be roles that have never been played. We'll call this relationship plays. And indicate this is an optional one-to-many cardinality. So if we move this over and we can see it better, we'll notice that the cardinality is opposite of what we need. So we'll select this line, go into the custom arrowheads, and change the direction of this. Make this the optional one-to-many, and make this the required one. And now we have that a role may be played in many organized events, and each organized event is for exactly one role. I hope this example for a rather simple situation gives you a better understanding of the basics of data modeling using entity relationship notation, the most common form of data modeling. You should now be able to handle similar tasks with more confidence. After reading both chapters on data modeling in modern database management, you will want to look at a second video that shows a more complex situation and the necessarily more detailed thought process for data modeling then. With these skills, you are developing capabilities that will distinguish you from many information systems professionals.